Okay, thanks so much. Yeah, I'm really glad to be here virtually. Um, uh, uh, um, uh, and to present this work to you today. I hope you find it interesting. And I'm going to talk about two related manuscripts uh, with many people over the past couple of years, including Professor Anand, who will speak tomorrow about some of our social ecological models, our coupled models that show regime shifts, but also Tim Lenton, who's here virtually, Martin Skeffer, R.I. Sujit, and Chris Fletcher. And of course, our students and postdocs who are doing the heavy lifting for much of this, like Tom Burry, Daniel Delusky, and Induja Pavitran. So I'll start off with early warning signals, and I'm pretty sure you've seen this a few times at this point. This is our paradigm for many early warning signals of tipping points, essentially a critical slowing down framework whereby when a system is in a state of high resilience, it has a very deep potential well, and it's hard to perturb. And so you see in panel C here, it rebounds very quickly. And in a panel D, it has a very low variance. But as the conditions change, as the environment changes, it shifts to a state of low resilience, whereby the ball could be more easily wobbled, and it could even go into a new state. And it takes longer to recover, which we see in subpanel E, and the variance is higher. So this has been applied to a wide range of systems very successfully. It's a very elegant theory applied to lake eutrophication, epileptic seizures, paleo-climate shifts, etc. But there are drawbacks, of course. So many of these indicators that flag critical slowing down have some drawbacks. They might provide false positives. They have limited capacities to determine the type of bifurcation approaching. In other words, they don't tell you much about the state that might lie beyond the tipping point. And they're based on qualitative changes in metrics, not absolute values. In other words, we see a trend going up, but we can't give you a p-value for how likely we are to result in a tip. Although there are some things you can do in that respect. So we have these drawbacks we have to contend with. Now, a different approach to modeling besides differential equations is deep learning algorithms, which are the opposite extreme, these highly complicated statistical models. And these are widely used, for example, to classify time series data. So if you have a Fitbit, for example, it can tell whether you're walking or running or biking just based on the time series of the heart rate versus time, and also your motion. And it does this by looking for features in these time series. So because early warning signals is all about picking up features in time series, these deep learning algorithms might be good at detecting critical slowing down and possibly other types of behavior that occur prior to each bifurcation type. And to be more specific, when we're looking at early warning signals, we can look on the right here for a second. And this shows the kind of mathematical equations where we get the idea of critical slowing down from. This shows a Taylor series expansion. And it's actually an infinite series, lambda 1 epsilon plus lambda 2 epsilon squared plus dot, dot, dot. And when we measure critical slowing down, we're looking at the first term here, the first eigenvalue, and that's shown in blue here. That shows that kind of approximation to the potential well. And as you can see, in a state of low resilience, that blue potential well on the right is a bit more shallow. And eventually the system tips. But of course, that's only an approximation to the actual state of the system. The actual state of the system here is a solid black line. And as you can see, it's a little bit different as you get further away from the current state. To capture those differences, we need to include the higher order terms of this Taylor series expansion here. The second order terms, the third order terms, etc. In fact, if we all add the infinite number of these terms together, we can get the actual potential, the black line exactly. But that's mathematically messy. and inconvenient, and so we drop those terms. However, these terms do influence the dynamics, and therefore we should be able to see their signature in the time series. And we think maybe deep learning algorithms could detect these very subtle signatures associated with second-order terms, third-order terms, and even things like flickering between basins of attraction. Anything for which our current mathematical theory is too elegant, maybe too simple to capture. So that's a nice idea, but the problem is that training deep learning algorithms requires lots of data, lots of time series, thousands and thousands of examples, and we don't have that for many real-world systems. For example, if you're studying lakes, you might only have 5 or 10 replications. If you're talking about the contemporary climate of the Earth, the world's climate system, we have no replications for what's happening right now. So what do we do? Oh yeah, and this is just a nice illustration which kind of shows that the system is converging to an equilibrium, and very close. It converges along this line, and the convergence along this line is determined by the simple critical slowing down phenomenon, that first eigenvalue, the first term of the expansion. But way out here, other things are happening that it doesn't detect. So we developed a couple hypotheses. So H1, if we train a deep learning algorithm on a sufficiently large training set, generated from a diverse space of models, the features of any empirical system approaching a bifurcation will be represented somewhere in that huge space. And by models here, I don't mean specific models like a lockable term model. I mean just random libraries of right-hand sides for the differential equations. So random models. Therefore, the algorithm will detect early warning signals in systems that are not in the training set. And that's crucial because, like I said, we don't have data from any systems. H2 hypothesis is that the algorithm will detect these early warning signals sooner than existing approaches like lag-1 autocorrelation, as well as tell us what type of transition is coming, which again, they don't usually do. Thus, even a relatively limited training set might contain the right kind of features that characterize these higher order terms that we normally ignore. So crucially, these hypotheses rely on universality, the fact that complex dynamics simplify in similar ways near bifurcation points, which is why magnetization of a material, for example, is not so different from ice freezing or a spatiotemporal shift in a vegetation pattern. So our approach here was to generate stochastic time series from a random library of models exhibiting a local bifurcation. We used some archaic software you might have heard of called XPP Auto. It was really difficult to get this to work because it's an old piece of software, and we're integrating it with Python. But Tom was eventually able to get that up and running. And then from Auto, we were able to take this random library of ODEs and find examples of fold, hop, branching point bifurcations, and no bifurcations at all for our neutral case. Branching points are like transcritical bifurcations. So then we were able to train a neural network, CNN-LSTM in particular. I'll say more about that in a moment, to classify the time series based on the pre-transition portion, fold, hop, branching, or neutral. So we train it on, we show it, this is an example of a time series before the transition, for a fold, for a hop, for branching, for a neutral. And so it looks for features that are associated with those four types. And then we looked for a bunch of test systems completely out of sample, nothing related, nothing at all to do with the training set, where the early warning signals were detected for a transition that had been subsequently observed and easily characterized. So these are systems where people have previously they studied these, they've observed some tipping points, and then they've observed early warning signals, and we found both empirical and model systems. So what is a neural network? It's basically a large statistical model where you have some inputs coming in, like these could be the residuals of a time series, and these can activate so-called neurons in the next layers, the hidden layers, and those in turn can activate neurons in the output layer. And the output layer might be, for example, yes or no, this is a transition or this is not a transition. And if you've seen neural networks before, we used a CNN-LSTM network. So that stands for convolutional neural network / long short-term memory network. It's basically two networks sandwiched together. The input layer first goes to the CNN model. That just stands for convolutional neural network. And what this does is it kind of scans over the picture one row at a time. And it applies these convolutional kernels, just like some of you, if you're a mathematician, you might have used them before, to look for features to determine, is this a truck, a car, or a van, if we're trying to classify cars, for example. And then that is passed in turn to a long and short-term memory network. And what those do is instead of, they're called deep learning because instead of having many layers in the middle, it kind of loops back to itself repeatedly. So the output becomes the input, as you can see in this diagram on the left here. And then finally, that gives an answer like this is a fold or a transcritical. So here are some examples of the systems we looked at. So we looked at the simple harvesting model by Bob May that Bob May studied in the 70s or maybe early 80s. I don't remember. And that's one of the simplest models. We looked at a consumer resource model, which illustrates two types of bifurcations here, with basically like X is the resource and Y is the consumer. And then we had the disease model, but it's coupled to human behavior. So we have the SEIRx equations that you might have heard of: susceptible, infected, recovered. But then we also have an equation X here, which represents imitation or social learning effects. And you might see more about this type of model tomorrow when Professor Anand speaks. We've worked extensively with these types of equations. So this model can represent vaccine scares, for example. For the empirical systems, we had some thermoacoustic experiments, and these were conducted by R.A. Sujit and Induja Pavithran. And basically, we'd have to ask them about details, but my limited understanding is that as you increase the voltage, you eventually cause sounds, and there's some heating of the element involved as well. And they have some very beautiful experimental data looking at this, looking at these effects that we were able to use for the study. Then we have some very different thing, paleo-climate shifts. We looked at 7 different climate shifts in the past, ranging from the end of greenhouse eras to the end of glacial periods and the desertification of Africa. And these have been previously studied for early warning signals by Vasilis Dakos. And then we looked at turnover in the Mediterranean sediments. The Eastern Mediterranean has gone through periods of oxic and anoxic states, with oxygen and no oxygen respectively, of course. And you can see these flips back and forth in the seabed in cores that are obtained from the seabed, especially. And so we also studied these transitions here. So here's an example of the types of output you can get from these models. The top row shows the residuals when you subtract the trend from the signal for fold, hop, transcritical or branching points, and no transition. And this is the pre-transition time series, of course. The second row is the deep learning prediction. The third row is the variance. So that's the classical early warning indicator. And the fourth row is the lag-mode autocorrelation. Now, the variance and the lag-mode autocorrelation, they trend up as you approach the bifurcation in all cases, except for the neutral case, as you would expect. So the deep learning algorithm acts a bit differently. So what it does is that far away from the bifurcation, it's not really sure what's happening. It predicts a null transition, so it's predicting no transition yet. But as it approaches the bifurcation on the right-hand side here, it's picking up more and more information from the first, second, and higher order terms. And And as it does that, it starts to change its classification. For example, in the case of a full bifurcation, the blue curve shoots up and it says, okay, I think this is a full bifurcation with some probability. In the second case, it says, okay, I think this is a half bifurcation. It's very certain about that. That's one of the easier ones to classify. And in the third case, it says, well, I think this is a transcritical bifurcation. And it also it stays neutral for the neutral one. So it's predicting quite far ahead of time, and it's telling us what type of bifurcation is coming. So that's basically how the predictions work. Now, to analyze the predictions more systematically, we generated these receiver operator characteristic curves, which is just a plot of true positives of the classifier versus false positives. So we kind of use this terminology. It's like a COVID test, true, false positives, because the classifier, it can give you true or false positive and also true or false negatives. Now, for a good classifier, you want a high true positive rate and a low false positive rate. So if you plot them against one another, and as you vary the discrimination threshold, whereby it makes its decisions about what's what, you should expect to observe that when the false positive rate is low, the true positive rate is high. So as soon as we start moving across the horizontal axis, we want it to shoot up to 100% in the perfect scenario. And then as the false positive rate increases, it should maintain a high true positive rate. So a good classifier should hug the upper left of the square on the right, whereas one which is basically worthless is basically doing coin flips. It goes along the diagonal. So we want something that's kind of away from the diagonal and hugging the upper left. And this is a way of capturing, both how sensitive it is, but also how specific it is. In other words, we don't want something that's always giving a positive. If it's doing that by saying everything is positive, we want it to give only true positives, not false positives. And so we use the area under this curve to measure how good it is, because when the area under the curve is 100%, it means it's perfect. And when it's 50%, it means it's coin flipping. So then we use these ROC curves. We compared them for the deep learning algorithm, Lagrange AC invariance, for predicting these transition types. And here's an example of what we found for the ecological model. So for example, in blue, we have the machine learning curve. In red, we have using the variance as an early warning indicator. And in green, we have the Lagrange autocorrelation. And as you can see, for the fold, hot, and transcritical bifurcations from these models, it's hugging the upper left quite closely in the machine learning case, which is what you want to see. And variance and Lagrange autocorrelation do okay, but they're not fantastic, and sometimes not much better than a coin toss. So it's working great for the ecological models. It also works very beautifully for the thermoacoustic data. You can see the blue curve is hugging the upper left. So it's giving you a lot of true positives and not so many false positives. And variance and Lagrange autocorrelation also do well in that case, but not quite as well, with a slightly lower area under the curve. And in the case of paleo-climate data, it's much more challenging to get a good fit. The machine learning model still does pretty well, but it's better than random, but it's also not as good as the other cases. Variance doesn't do well at all, and Lagrange autocorrelation does pretty well, about as well as slightly better than the deep learning algorithm in this case. And I'll come back to the climate system later and why that might be different. And finally, for the Mediterranean data, it does extremely well. It's hugging the upper left here again, outperforming variance and Lagrange autocorrelation. And then this is a vaccine scare model, and this one is kind of interesting because we can look at any variable we want to because it's theoretical. So we have one ROC curve for the I variable on the left, and one for the X variable, which represents pro-vaccine sentiment on the right. And here the tipping point corresponds to a vaccine scare for a pediatric vaccine like measles. In the case of the I variable, we see that all of the approaches struggle. In the case of the X variable, we see that the machine learning algorithm outperforms everything else. Now, this is interesting because for two reasons. First of all, what's happening here is that this vaccine system is so-called reactive or non-normal. If you're a mathematician, that means your eigenvectors are almost parallel. If you're not a mathematician, don't worry about it. It just means that you have two very different timescales in the system. One is the timescale of opinion, and one is the timescale of vaccination. And the vaccination timescale is much, much slower than the opinion timescale. And the reason is that if we're thinking about measles vaccination, you get vaccinated once when you're a kid, and that's it. So the vaccination rate is at the population scale is very low because it's only some kids getting vaccinated every year, 12, 18 months, 3 years old. But opinions can change very rapidly, and people who are vaccinated, as children, 30, 40, 50 years ago might change their opinion, and everyone is potentially discussing this. So the timescales are very different, and that changes the early warning signals. In the case of the vaccine model, it means that if you're monitoring infected cases, you can't detect the vaccine scare. But if you're monitoring pro-vaccine opinion, for example, through social media, you could see it coming a mile away and perhaps even predict outbreaks much better that way than by just monitoring infected cases. So this is an interesting application of early warning signals in these coupled systems. And we also observe as expected that as you add more and more data, the systems, the classifiers all improve. So the left-hand side here shows where you're using the last 20 to 40% of the time series before the transition. And then the right-hand side shows the last 0 to 20% before the transition. And as you can see in all the cases, when we're using more data, we're more confident as we would expect. Okay, but I noted how much the algorithm struggled with the paleo-climate data. And so, this is interesting for two reasons. First of all, when the algorithm is struggling, that's an opportunity to improve it and learn something new and to generate some new research questions and make progress. And the second reason is that, climate change is obviously a pressing issue, and it would be good to know, are we kind of looking at more of a runaway greenhouse effect, or is it going to be a smooth transition? Will it be patchy in different places, etc.? So we decided to look at this more carefully next. And if we look at the current evidence for contemporary climate tipping points, we basically at the moment have two lines of evidence on the right here. The first is empirical data, looking at paleoclimate shifts from ice cores, for example. And the advantage is that this data is empirical, so it's ground truth. But the con is that the nature of forcing in the past does differ from the nature of forcing now. Past shifts have been influenced by the tip of the Earth's axis, for example, but the current forcing is caused by a massive and essentially sudden release of CO2, sudden on geological timescales, into the Earth's atmosphere. So it's different from those past climate shifts. On the other hand, we have sophisticated mechanistic models that are based on large mathematical simulations, like general circulation models. The advantage is that we have a mechanistic predictive approach here, and you're putting in our best knowledge of the climate system to make it as accurate as we possibly can. But the con is that it's still just a model, and we don't really know if we're including all the relevant details. So there's still room for some uncertainty there. So what we're trying to do is develop a third orthogonal line of evidence. Our hypothesis is, directly from the early warning signal literature, the information is in the noise. So the information about what's going to happen in the future climate, the answer about what's going to happen in the future climate is already present in the noise we're seeing right now. We just have to know how to read it and how to understand it. And we think that if it is a tipping point, looking at machine learning approaches on these libraries of bifurcations might give us information about what will happen. So that's the advantage. You can predict based on present noise. You don't need data from from the system, and we can't get it anyway because this is the first time this has ever happened. The con is that we need a big enough bifurcation library, and you have to be sure that the relevant bifurcations are included in that library. So for our training set, in this case, we're moving to a spatiotemporal regime. And we're using something, we're always trying to use something a bit different from what the system we're studying is, something that kind of represents a whole bunch of different possible transitions. And we're using these lattice models of magnetic dipoles interacting with nearest neighbors. This is an Ising model or an Ising model. And these show, two types of phase transitions, these continuous second order transitions, whereby the transition is smooth, and also the first order or discontinuous sudden transitions, where it's a very different and sudden transition. Like this is, for example, water freezing. It's very sudden. The water's cold, 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 and then it freezes all of a sudden. And this particular model that we're using exhibits a lot of critical behaviors that represent a broad class of transitions. And they show things like increases in spatial and temporal variance and autocorrelation. So it shows some of those features that have been studied in other analyses of early warning signals. Now we're going to use the spatiotemporal system to do a spatiotemporal training set with a spatiotemporal algorithm. And so we used this classifier based on the Ising model. We looked at 3 climate relevant test models. One is a coupled vegetation water system of desertification, which shows a transition as global rainfall falls below a certain threshold. So this is by Sonia Kefi et al., who of course is also a speaker this week. And then we looked also at a sea ice percolation model, where you have basically a melting ice sheet. And as it melts, you create these gaps in the ice through which sea ice percolates through the porous medium. It's like a sponge at some point. At some critical temperature, these sponges, these cells in the sponge connect up, and the water can go all the way through. And then we looked at these massive CMIP-5 simulations. So these are climate simulations from big models, and they're available at a library. You download the transitions and classify them. And so here are the results using both the second order and first order Ising model classifiers for the vegetation system by Kefi et al. And the percolation system. And as you can see, it's doing pretty well predicting these transitions in these systems it's never seen before, with area under the curve around 70 to 80%. And it does okay whether you're using, just the spatial classifier in green, just the temporal classifier in red, or both together. So that's good to see. Now for CMIP-5, we have some success and some problems. So for example, for some of these acronyms, these massive acronyms which mean different things, CMIP-5 is just a big library of different climate systems, like collapse of the Gulf Stream, collapse of the circumantarctic current, collapse of the Amazon rainforest, etc. Different regional scale climate systems, and we can see that in some of these cases. I'll say more about what these mean in a minute. It's doing pretty well again. It's hugging the upper left fairly well, but in other cases it's basically doing a coin toss. So we looked more carefully into what these different systems mean, and we broke it down by terrestrial green, land cryosphere, so the ice caps, or Greenland ice sheet, for example, orange, blue is atmospheric systems like cloud cover or the global temperature anomaly, and red is the ocean cryosphere. So that's ice sheets over the ocean. And you can see that it does best for green, which is the terrestrial systems, which maybe isn't too surprising because that Ising model does look like a lot of terrestrial models you might have seen before. And it struggles the most with blue and orange, which are the cryosphere models. So there's something about cryospheres, these ice sheets that we're not representing in our training set. That's what this tells us. So we're now expanding the test to include satellite data. So we want to test empirical vegetation data like the Amazon rainforest and Sahel in order to see that, well, will the classifier predict empirical transitions in these systems, especially along a spatial gradient. And I don't have much to show about that yet. So starting to wrap things up here. So what are it's important to think about the limitations and to be aware of the limitations of this approach. The first limitation is that this is not some magic formula. I think the dream of a lot of computer scientists is that we can come up with a big enough computer algorithm that can predict everything, right? And you don't need subject-specific expertise anymore. We can get rid of epidemiologists and biologists because the computer will do everything. And we're pretty far from that still. The important thing to keep in mind is that the bifurcations present in the empirical system must be represented in the training set library. You have to be confident about that. In other words, the answer provided by the algorithm it could mean anything. So this approach does not mean we can ignore subject-specific expertise. We still need that expertise to tell us what should go into the training library, what tips might be relevant for the system. And this is a reflection of a more general phenomenon which has been observed before. We often observe that when we're dealing with messy, complex systems like biological systems, social systems, etc., if we kind of hybridize a purely statistical or machine learning approach and a purely mechanistic approach, we often do better that way because you're combining the best of both worlds. And that's kind of the same spirit of this work. So in conclusion, combining, hybridizing machine learning and complex systems theory it shows a lot of strong potential to provide early warning signals of climate tipping points and other tipping points, as we've seen. We can have a spatiotemporal classification. It gives us better sensitivity and specificity than the classical existing approaches, the kind of workhorses, Lagrange autocorrelation and variance. It might give more advanced warning. We haven't studied that carefully yet, but that's also an area of research. Can it pinpoint the time of the transition better, and can it provide more advanced warning? And crucially, it can tell you something about the state beyond the tipping point. It can't tell you exactly what's happening, but it can say, well, it'll oscillate, or it'll collapse suddenly, or it will be continuous. It can't tell you that. So that's useful information. But much work remains to be done. We have to figure out, most of the work, a lot of the work is just what transitions need to be included in the library, and how do we get them, and also, which algorithms are best for climate systems and for other systems, because the answer may vary. We can't always use CNN-LSTM, so there might be better algorithms out there. For example, EWSnet is I can't remember where that is in the schedule. You might have already heard about it. Oh yeah. So one final thing. So we're hiring postdocs to work on this approach, and we have funding to look at droughts, early warning signals of droughts, such as might be caused by failure of the monsoon. And so we're looking for postdocs based at University of Guelph School of Environmental Sciences with Professor Anand, who you're going to hear from tomorrow at the same time, and with me as a co-advisor. And I don't know who's out there in the audience. Oh, I have a picture now. So if you are interested, or if you know people in your lab who might be interested, please do contact us. So that's all I wanted to say. I guess pretty late there, so I wanted to leave a bit of time for questions. And I apologize if the audience is diverse and I got a bit technical at times. I'm glad to unpack any of that if anyone's interested. So thank you very much for listening, and I'm glad to hear some questions and discussion.
Thank you, Chris, for a very, very clear talk, and it's time for questions now. Yeah, go ahead.
Hello. Hi, sir. It was really nice presentation and very nice results. I have a few
Thank you.
questions. One that in the deep learning approach for the temporal classification, you classify bifurcations, fold bifurcations, transcritical and Hoff. Right, sir? Sir, just
Yes.
out of curiosity, is there any reason for not considering pitchfork?
Oh yeah, that's a great question. Yeah, we excluded that. Why did we exclude that? It's been 3 or 4 years now. But there's you could do pitchfork as well, and it can do pretty well at predicting pitchfork bifurcations. I think the reason we didn't include it is because it gets harder and harder as you throw more bifurcation types into it. Any kind of n-way classification problem is harder as n increases. And for the types of systems we had in mind, these empirical study systems, we didn't see examples of pitchforks in the data. So we thought it just wasn't, it didn't add much value, but you can definitely do it. It will work. We also have experimented with global bifurcations, like we looked at a oh geez, what was it? A homoclinic bifurcation. And it actually does pretty well at the homoclinic bifurcation. We're not totally sure yet because there is no critical slowing down before a homoclinic bifurcation, but it can do it really well. Probably because it's looking at stuff happening a bit further away from the equilibrium as the system is wandering around in phase space. So yeah, that's the long answer to your question. It wasn't too relevant for our study systems, but you can do it and it would work. Thank you.
Okay. So one more question is that, so when you test an empirical data, how do you decide the ground truth labels?
Yeah, so for our first study, we decided it because based on what actually happened, right? So these are all systems where we saw the tipping point happen. We saw the greenhouse era end. Or we saw the thermoacoustic experiment, we saw the end result. And so it was actually pretty easy in that case because it's directly observational. Now for the second case where we have for example, the CMOT5 simulation, it's more complicated because we have these complicated simulations. They're so complicated, no one, even the people who design them and run them, they don't really know what's happening behind them. So you'll have a simulation where suddenly the Amazon collapses, but it's not very clear. Is that a fold bifurcation or is it something else? Maybe some weird dynamical phenomena we don't have a name for. And in that case, we determine ground truth. We still have the simulations, but we have to kind of classify them into just transition or no transition because we can't call it a fold or hop anymore. So we still have a solid ground truth in that case, but it's not as strong in those cases.
Okay, thank you, sir.
Thank you.
I have a question. So one of the, in many ecological systems, stochasticity is a really important driver, right? And then you can have abrupt transitions entirely induced by noise. And so let's say, in fact, we found in one of our studies that a grassland transition was actually driven by stochasticity away from a bifurcation point. So because your network is not trained on such a transition, it would probably pick one of the three, right? Or maybe even a no transition case. It may even pick probably no transition, right?
Yeah, exactly. So it will give you an answer, but the answer doesn't mean anything because it doesn't have any knowledge of whether it should be certain or not, right? So there's no kind of meta there's no introspection involved. So that's why we still have to think about what are we putting in the library. And I'm glad you brought up noise and noise-induced transitions because how you pick noise is crucial too. We just did Gaussian noise, but of course you could, if you have colored noise, it's a totally different ball game, and many systems do have this colored noise. I believe Smitha's model, they look at colored noise. So so that's an important thing to consider for many systems.
Yeah, thank you. Any Valerie? Yes.
Interesting talk. My question is about the paleo transitions that you say that the model didn't perform well. I presume it's because it's kind of 50 points there, maybe 70 points, sometimes 100. Have you performed a systematic experiment with some model data where you would increase the amount of input data and see how your algorithm performs and responds to variability in the input data for detection? Thank you.
Oh yeah, thanks. That's a great question. We did some experiments with simulated data, and we found that, as expected, if you have more data, more than you need at the bare minimum 50 to 100 data points for it to give you a decent prediction. And as you increase the data, it got more certain. So yeah, certainly the one reason for the poor performance on the climate data might be that we often only had 50 to 100 data points, maybe up to several hundred in a few cases. And in fact, we had one data set where we had 20 data points. We just couldn't do it. We didn't even try because it's too short. So yeah, so like, for maybe many contemporary climate systems, maybe we'll be pleasantly surprised in that, we in principle, at least for something simple like the global temperature anomaly, we can have, excellent data, 1,000 data points or more. So that might help us a little bit, but I suspect as well that, there are also some complications going on here that we have to get our head around, and that's why we have, climate scientists involved too, to help inform that aspect of it.
Any other questions? Yeah, I just had one comment. I really appreciate your last comment that we do need to combine deep learning methods with mechanistic modeling or mechanistic based understanding, because otherwise we don't know what it gives us back. It can only give us back what we trained them for, right? So I think that's something useful for any application of deep learning, and I appreciate your sort of summary that emphasizes that point. So if there are no more questions, let us thank Chris again for a very wonderful talk, and